Hey guys, it's kind of crazy. We've made it to our last section and lesson of the calculus school year. It's kind of ironic to me that we're ending it on a conversation about exponential growth and decay with everything going on in the world around us. But here it is. So let's get going. The first thing we're going to talk about is separable differential equations. So if we have an equation like this, dy dx equals f of y, g of x, that's a g. I don't have any white out here. Thank you, quarantine. This is called a separable equation. And what it means is that we can separate the variables so that all of the y's are on the one side and all of the x's are on the other side. So the solution is found by anti-differentiating each side with respect to its isolated variable. Another way of saying that is that all of one side needs to be in terms of x and all of the other side is in terms of y. Okay. The other note for this is dx and dy cannot be in the denominator. So you need to move, for example, right here, we need to be able to move our dx over to this side so it's not in the denominator. Okay. All right, so example. Solve for y if dy dx equals the quantity of xy squared. And we know y equals 1 when x equals 1. Note for you on these problems, we will not use this point right here, 1, 1, until the very end. So you can't just plug it in. That's not just the answer. Okay. All right. So what we're going to do is we need to, in the end, get rid of this dy dx, which is has to do with our integrals. Okay. So we're going to have dy dx equals here. We're going to give this squared to both of our pieces. All right. We're going to move things over so we have y's on one side, x's on the other side. So we're going to have dy over y squared equals x squared dx. Okay. Now we're going to take the integral of both sides. So in order to do that, I'm going to maybe write this as a negative exponent just to make it easier. So y to the negative 2 dy equals x squared dx. And now I'm going to take the integral of both sides so we can get rid of this dy and this dx. Okay. So when we take our antiderivative of this, we're going to go up 1 to a negative 1. Okay. So then we would need to drop a 1 over negative 1 in front of this. Okay, let me check that out when we get there. Okay, so let's differentiate the other side. We would drop this up to an x cubed, which means we would need a 1/3. So yeah, we would need a negative 1 over here. Okay. Our dx went away. It might be easier if we move this negative 1 to the other side for when we solve. The other thing that we need is Cassandra's rule right here. So we have to have a plus c. We don't know which side it goes on, and it doesn't matter. It usually goes on the side of x. Okay, so we're going to move this negative over here. So we'll have we will have y to the negative 1 equals negative 1/3 x to the third plus c. Okay. This is going to be the same as 1 over y. Usually when we solve, we have a y equals equation. So we're going to flip these two so that we can have it in terms of y equals. Okay. So now what we can do is use this point of 1, 1 and plug it into our equation so that we can figure out what the plus c is going to be. So we'll have 1 equals 1 over times 1 plus c. Okay. So then we'll need to solve. So same thing, we could flip it, negative 1/3 plus c equals 1. C is going to equal 4/3. So we'll plug that back into our equation right here. Okay. We will have y equals 1 over negative 1/3 x to the third plus 4/3. Okay, we don't usually want a fraction in the denominator, so if we multiply the whole thing by 3 over 3, we'll be able to get rid of those denominators. So now we'll have y equals 3 over negative x cubed plus 4, or we could write it as 4 minus x to the third power. Okay, so that would be our equation at this would be our equation if we solved for y. Okay. Have I been working and you couldn't see it? Of course. All right. In the book on page 394, it'll show you a way that you can check your work if you want to. I'm just going to leave it as is. Okay. All right. We're going to talk about a bunch of different laws today. So I'm going to show you those. So this next one is the law of exponential change. The law of exponential change says that y equals y0 e to the kt, where k is the growth constant if k is equal to 0, or it's a decay constant if k is less than 0. y0 is going to be your initial value, and t will be your time, and then k is going to be your growth constant. So this is something we're going to start using in our problems, the law of exponential change. All right. Okay. So another note for you is that population is exponential growth because we're talking about growing. Okay. When we're talking about it, we'll something that might pop up, just kind of heads up, change of population over change of time equals the percent growth of our current. So just kind of a thought to tuck away for you. Okay. Other thing we're going to talk about today is compound and compound continuous interest. This one's also interest. All right, so these are two different equations. So this is if we compounded something, let's say we compound our interest daily, weekly, monthly, biannually. All right, we'd use this equation. This is if we compound our interest continuously. So our interest is constantly being accrued to our equation, right? These are what the different components of our equation mean. I'm not going to talk about that long because you have a chance to peek at those. All right, so an example for you. It says, suppose you deposit $800 into an account that pays 6.3% annual interest. How much will you have 8 years later if the interest is compounded quarterly and compounded continuously? So for compounded quarterly, we're going to have to use this first equation. Okay. A of t is our amount over time. Okay. AO is our initial amount, which it says we deposited $800. R is going to be our rate, which is 6.3%. We need to change that to a decimal, so it'll be 0.063. Over K is the number of times it's compounded. So it's compounded quarterly, which means it'll happen 4 times a year. Okay, and then that needs to be our K again, and the time, and we're talking about over 8 years. So this equation right here, you legitimately just need to throw this into your calculator, and it's going to do the math for you. So hopefully you can see what my calculator says. 1 plus 0.063 divided by 4 to the, when you do your exponent, make sure you put it in parentheses so the whole thing becomes an exponent. So if we compounded quarterly over that time, our new amount would be $1,319.07. So AT would be $1,319.07. All right. If we compound continuously, we can use this equation, our continuous equation, and let's see what the amount is to compare. So our AO is going to be 800. E, that's, remember, a number, so E is not going to be anything. It's going to always be E. Our rate is 0.063 and a time of 8 years. So let's plug that into our calculator. E is going to be a number, so it's on your calculator somewhere. Mine is over here underneath the ln. Okay, and that's going to be 13, 24, 26. So with this amount of money, it only increased about $5. Okay, but with greater amounts of money, it's going to be a greater difference. So in the end, maybe the difference of them is, well, we could do it. The difference of them is going to be $5.19 difference. Okay. But imagine on this one if we put in $8,000 instead. Okay, the difference would be a lot bigger. All right. Next thing we're talking about is radioactivity. So radioactivity has to do with, we're mostly talking about radioactive decay and how long it takes something to decrease in radioactivity. So this is our equation for radioactivity. Okay. Half-life is the time it takes for half of the substance to be present. So we're going to work on this equation, and it's going to tell us that we need to find the half-life of a radioactive substance with a decay equation of this, and show that the half-life depends only on K. So we're going to manipulate this equation pretty much to solve, to see what is left over time. All right. So when we talk about half-life, that means that this Y is going to be half of our initial value. So y equals half of yo. So what we can do is substitute that in. So we're going to put 1/2 yo equals yo e to the negative kt. Okay. The y's are both on both sides, so they go away. So what we have left is that we have 1/2 e to the negative kt. Okay. In order to get rid of an e, what we can do is take the ln of both sides, and that'll pull this down. So we have ln of 1/2 equals negative kt. Sorry, my writing is shaking the camera a little bit. Right? If we wanted to get it in terms of time, so find the half-life, so find the time. We want to get time by itself. So we divide by negative k. So our time is going to be equal to negative 1/k ln of 1/2. Okay. Using ln rules that we know when we do log rhythmic functions, we know that ln of a of 1/a equals negative ln of a. So we can change this piece right here into negative ln of 2, which means that in the end our equation is going to be ln of 2/k. So the time for half-life just depends upon the ln of 2 over whatever k is, which I show you right here, the equation for half-life of a substance. K has to be greater than 0, and the half-life is going to be ln of 2/k. All right. 3 more examples. Next example, finding a base. This is on page 358. It's example 4. I'm telling you that because it has lots of words, so I'll read it to you. But I'm not going to write them all out. So it says, it's about choosing a base. At the beginning of the summer, the population of a hive of bald-faced hornets, which are actually wasps, is growing at a rate proportional to the population. From a population of 10 on May 1st, the number of hornets grows to 50 in 30 days. If the growth continues to follow the same model, how many days after May 1st will the population reach 100? So I put the important information on here. We have 10 wasps on May 1st, 50 in 30 days. If the growth continues the same model, how many days after May 1st will it reach 100? Okay, so we're going to use this magical equation to help us figure out what the base is. This is just an equation that we know from exponents. Okay, so into this equation we are going to plug in, okay, A, we know that we have 10, that's our initial amount, times b to the t. Okay, we don't know what that is. We are going to set this equal to, that we know 50 in 30 days, so we know 50, 10 b to the 30, and now we can solve and get ourselves a base to then solve the exponential equation. Okay, so we'll divide by 10. We'll have b to the 30 equals 5. Okay, we are going to multiply both sides by the 1/30th power, or taking the 30th root from both sides. Okay, so that's going to be our base, is going to be b to the 1/30th, is going to be 5 to the 1/30th power. All right, so now we can use that information to plug it back in to this equation. So we'll have y equals a, which was our initial, 10. B is our base to the time. Okay, we want our final amount to equal 100. All right, so we'll start solving. Get rid of that 10. Okay, in order to, at this point right here, we could actually get rid of our parentheses and multiply these. Make this t to the 30th. All right, that's fine, we can combine those. No lose. Okay. Now, in order to get this down from here, we can take the ln from both sides. So we'll have ln of 10 equals hold on. Oh, okay. We gotta go t over 30 ln of 5. It's just a logarithm rule. If you take the ln of the side, this can pop down in front times the ln of 5. So we'll divide both sides by ln of 5. Okay, so we'll have over here ln of 10 ln of 5 equals t over 30. Get t by itself. Okay, so we'd have 30 ln 10 over ln 5. We're going to plug that into our calculator to find how much time it'll take. Okay, what's probably going to be the hardest about these problems is that we're going to have to use some of these logarithmic rules. So that's probably going to be one of the harder things. So if you have a question or you need to look something up, that would be a good thing for you to do, and I totally understand. Okay, so the time it's going to take is about 42.92 days, or we could say 43. Okay, all right, next problem. Scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample that has decayed 10%. Okay. So we're going to need to use our equation from before. And we know that let's see, let's write out our equation. We have a of t. I gotta go back to the half-life page because I don't have it all memorized in my head. Okay, y equals yo e to the negative kt. Okay, we remember when we're talking about half-life, we know that y equals 1/2 of yo. So 1/2 yo equals yo e to the, sorry, I'm just making sure that I give you guys all the right information. Just is more weird when it's over a video than in person. Okay, because let's see. So now we are just using a different equation. Okay, it says we're going to model our exponential decay. Oh, because we don't know a base, so we can't use this equation because this equation is telling us that we have a base of e. Okay, so I need to use an actual exponential equation that helps me to find a base. All right. Okay, so we are going to use the information from above to build our equation out. So this equation, okay, we know that y is going to equal 1/2 of a Okay, but we don't actually need that information because we're not working with half-life. We just know it's half. So this half-life information is just going to be what our base is because we know we're working with a half-life. We actually know that this amount right here needs to be 10% of the original. So we're actually going to do 0.9% of A equals A times 1/2, right? And our t is going to be t divided by 5,700 because we don't know how much time it's going to take to get to this amount. All we know is that it's going to be some form with doing that with that 5,700. Okay. So now we need to solve for this equation to find what the value of t is going to be. So what we're going to have is we're going to have our a's are going to go away. Okay, so we're going to have 0.9 equals 1/2 t to the divided by 5/7. All right, we're going to be able to take the ln of both sides. When we do that, this drops in front. Okay. So now we need to get t by itself. So we'll move our divide by ln of 1/2. We'll move it to a decimal just so it matches. So we'll have ln of 0.9 divided by ln of 0.5 equals t over 5,700. Okay, then we'll multiply both sides by 5,700. ln of 0.9 over ln of 0.5 equals t. Hey, this is another, throw it into your calculators. Good thing class is over, almost over, because my calculator's battery's dying. Okay. Oh, I inputted something in wrong. Okay, I think it's this part right here. ln of 0.9, insert parenthesis. Okay, so we got 866. So we'll say it'll take approximately 866 years to get to 10% of the substance gone. or 90% of the substance there. Okay, kind of crazy. That's why radioactive material is something you don't want to mess with. All right, last problem with a bunch of information on it. Newton's law of cooling tells us, it talks about how long it's going to take something to cool down. Okay, T is the temperature of the object at time t, and Ts is the surrounding temperature. So for example, if you cook pasta and then you put it in, or let's say you bake cookies and you take them out of the oven, the temperature in the room is going to impact how fast they cool down. So that's what this Ts is relating to. You can use this equation only if we are at 0 degrees Celsius, wherever the surrounding temperature is. Okay. All right, so let's work on this problem. Hard-boiled egg at 98 degrees Celsius is put in a pan under running water of 18 degrees Celsius to cool. After 15 minutes, the egg's temp is found to be 38 degrees Celsius. How much longer will it take for the egg to reach 20 degrees Celsius? So obviously we're going to have to use Newton's law of cooling. Okay, so our T, we don't know what that is. Our Ts, our running water, was 18 degrees. Okay, and that got us from 98, our initial amount, minus 18. Okay, we don't know what our K is, and we don't know what our time is. Okay, this is just the original equation with all the information we know. Okay, the goal is that we're going to have to find out what the K is in order to solve the rest of the equation for us. So we know what the temperature is at 5 minutes, so we can use that to find K to then find out when it'll be 20 degrees, right? So after 5 minutes, we know our T is 38 degrees. Okay, we can simplify this to 80. Okay. 18. But why? Okay, hold on. Okay, so I would do this. Okay, so now let's solve. So I'll have 1/4 equals e to the negative kt. Okay, so now ln of both sides, ln of e makes sure this just cancels out. Okay. Whoops, I know this 38 happens at a time of 5 minutes. So it's okay, hasn't impacted us yet. Okay, so then let's get rid of our -5. K equals whatever this is plugged into our calculator. If you remember the rule before, to get rid of this negative, ln of 1/a equals negative ln of a. We could make this ln of 4/5. That'll pop out a negative and a negative, so then those will go away. Okay, that's going to be what our K is. Do not round. You need to use this number. If you don't use this number, then you're going to potentially throw off your time. Okay, so that's our K. We can plug that back up here into our original equation, all right, to help us to figure out when our t is going to equal 20. So this t right here. So we'll have t minus 18 equals 80 e to the negative ln of 4 over 5 t. All right. We may want to add this 18. May want to reduce this to negative 0.2 ln of 4 t minus plus 18. All right. Because we don't have a way to solve this, what we're actually going to do is solve it graphically. So we're going to find out when this equation intersects with the line t equals 20. I have a low battery. Hold on, I don't want to lose you. Whew. Okay. You guys know all about my low battery, so it's all good. T equals 20. All right. So I'm going to throw those two things into my graphing calculator. So I'm going to throw in t equals 80 e to the negative 0.2 ln of 4 times x. We're going to find when that equals 20. We're going to graph. Okay, it's way over here somewhere. And we want t equals 20, so we know that we probably don't need any x's. We need our y's at least to be at 20. That's 25. Okay, and then we don't need any x's, and we need to go over to the side with time. We know this was 5 minutes, so maybe we'll make it just like 50 just to give us a lot. Okay, it's going to draw lines. So we need to find out when these two intersect. So we could trace, or we could go second calc, intersect. Is this the first curve? Sure. Yes. Guess. Okay, they intersect at x equals 5, y equals 20. Which, does that make sense? No. What happened? Oh, I didn't add this plus 18. Okay, that didn't make any sense because in our equation over here, it took 5 minutes for it to get to a different amount. So there you go. Intersect, second line, first line, guess. There we go. So at about 13.3. So our time is approximately 13.3 minutes for it to get to 20 degrees. Okay, we need to find the intersection. We can use second calc intersect. Okay. All right. Okay, that's it. So much stuff, I know. Here's your homework assignment. Page 361, 3 through 18 multiples of 3, 19, 21, 24, 31, 37, 49, 50, 52. I will send you the answer key so you can check these out. This will be due to me on Tuesday. I will also be sending out to you your review and your extra credit assignment. That will be your assignment for Tuesday, and then your test is next Thursday. On Tuesday, if we could meet briefly at 1:30, we can talk about AP test stuff. If 1:30 is not going to work, please let me know. All right, you guys, have a wonderful day today. I will talk to you later. Bye.